We're going to go ahead and get started here with our review for the Rube Goldberg test, which is going to be a basic overview of a lot of the major ideas we did throughout the year this year. It's not going to include every single little topic, but it definitely will focus on the things that came up time and time again. So we'll start here with our first topic, which was kinematics. And so we're just going to start with going way back to one of the very first things we talked about, which is the three ways for an object to accelerate. And that is an object can speed up, an object can slow down, or an object can change directions. And acceleration really measures how quickly that process occurs, how quickly we speed up, slow down, or change directions. With that, connected to acceleration, we have our four kinematics equations. We have our delta x equation, we have our v final equation, our v final squared equation, and then our other delta x equation. Now you're going to be given these equations on the test, so there's certainly no need to memorize these, but I just like to go over the equations and make sure that we're familiar with them leading into the test. All right, a few tips for solving these problems. I always think it's important to set up that chart right off the bat with all five of the variables, delta x, vi, vf, a, and t. And for me, that helps kind of determine what I know, maybe what I need to reread the problem for to get, and ultimately what equation to use to solve for whatever I'm looking for in the problem. Keep in mind we always need three numbers to find a fourth, so that's really your goal, is to try and find three of those numbers, and that will allow you to solve for a fourth one. Be careful with your signs, that's always important, but we want to be consistent, and if velocity and acceleration are in opposite directions, then they better have opposite signs. And on top of that, think about numbers that you might know even if the problem doesn't explicitly say it, right? Like if something starts from rest, that means your initial velocity is 0, even though it doesn't say your initial velocity is 0 explicitly. Lastly, let's talk about free fall, which is an example of kinematics, an example of accelerated motion. And let's talk about some concepts that we know here for free fall, thinking about an object that starts here, goes up in the air to its peak, and then falls back down, landing ultimately below where it started. So what concepts do we know? Well, the most important one we know is we know that our acceleration is going to be negative 9.8 meters per second squared, which is little g. Okay, if you only know one thing about free fall, you should know that all objects, regardless of their speed, etc., accelerate downwards at 9.8 meters per second squared. Some other things we know at the peak, our velocity is going to be 0. Okay. We also know, and the following ones are going to be true only if the launch is symmetrical, meaning that it returns to the same height from which it was thrown, so just going from here to here. But there are a few additional concepts that we know in those situations, such as at the peak, our time is half of our total time. Okay, being the symmetrical launch, the time to go up and the time to fall back down are identical. We also know, if it's symmetrical, that when it returns to the spot where it was thrown from, its delta x, its displacement, is going to be 0, and its velocity is just going to be the negative of the initial. So if you throw something up at 10 meters per second, when it returns to that spot where you threw it from, it will be traveling down at 10 meters per second. Okay, so those last three are only true if our launch is symmetrical, if we return to the same height that it was thrown from. But those are useful ones when we do have a symmetrical launch. All right, if we land though up here above where it was thrown from, or down here below, then these three are not valid. Moving on to our next topic, which is forces. We'll start with Newton's laws, which are really the basis for all of forces. And so what I always say for the first one, this is the objects at rest stay at rest and objects in motion stay in motion law. But I always say that objects need an unbalanced force in order to accelerate. Okay, so if objects have an unbalanced force, they will accelerate, they'll change something about their motion. If they don't, they'll either continue with a constant velocity or remain at rest. The second law is just F equals ma, but it does tell us about how those three variables are related. Mass and acceleration are inversely related, force and acceleration are directly related. And then lastly, we have Newton's third law, which is that forces come in equal and opposite pairs. Okay, so the force that A exerts on B is the same as the force that B exerts on A, just in the opposite direction, so it's negative. We indicate that with our sign, of course. Moving on to some tips here for solving some of these problems, just basic tips. Number one, we always want to draw a picture, draw that free body diagram. After that, we're going to set up our max and may, set up our F equals ma in both the x and the y directions. If there's any forces at angles, we're of course going to break them into their x and y components like we do with any vector that's at an angle. And then keep in mind that acceleration links forces to kinematics, and once again, we want to be careful with our signs. Let's move on now to talk about some specific forces that we should know. So we'll start with gravity, of course. We know that gravity is equal to mass times g, which is 9.8 meters per second squared. And gravity, as we know, is basically always there, and it always points down. The next force we have is the normal force. The normal force is a force that results from any surface. And the reason why it's called the normal force is it's always perpendicular to that surface. We don't have a formula for finding normal force, but we do know that it comes from a surface and it's always perpendicular to it. Next force we have here is the force of friction, and we actually have two ways of finding force of friction because we have two different kinds of friction. So the first is kinetic friction, and kinetic friction is going to be equal to mu k, the kinetic coefficient of friction, times our normal force. The other friction we had was static friction. That would be the not sliding friction, and in that case the formula is the force of friction is less than or equal to mu s times our normal force. Okay, so keep in mind that mu there is that coefficient of friction, and friction either opposes the direction an object is sliding, if we're talking about kinetic, or the direction that an object wants to slide, if we're talking about static. A few tips here for solving these friction problems. First of all, when we're doing these, we want to set up max and may, some of the forces in the x and y direction. And the reason we need to do that is we usually need to use our y forces to solve for the normal force. Normal force plays an important role here. Force of friction depends on that normal force. So we're usually going to have to use our y forces to solve for the normal force and then transfer that over to our x forces. One important thing to remember is we shouldn't assume that the normal force equals the force of gravity, although that sometimes is the case. That's not always true. And so we need to make sure we know for a fact that those two are equal and not just assume that they are. And the last thing is for static friction, keep in mind that when we do mu times the normal force, that gives us our maximum possible force of friction. But the actual force will be less than or equal to that maximum possible force. Next we're going to talk about inclined planes. So let's first think about the forces acting on an object on an incline. We know we have the force of gravity, of course, going straight down. We're also going to have the normal force going perpendicular to our surface here, Fn. And we do this little trick here with inclined planes where we tilt our axis. So we take our x-axis and we make it parallel to our incline. We take our y-axis, we make it perpendicular to our incline. So that's the first tip we're going to have with inclined planes. And then what we notice is that gravity right here is going to be at an angle. So what we're going to do is we're going to break that gravitational force into its x and y components. And whatever angle that incline is tilted at, that will also be this upper angle here in my triangle. So that means that my x component will be fg sine of theta, and my y component will be fg cosine of theta. Last force we have here is the spring force, which exists obviously whenever there's a spring, and so that's given by kx, where k is our spring constant, and x is the distance the spring is stretched or compressed. We'll next move on to circular motion, and we're really going to focus on uniform circular motion here, which is circular motion at a constant speed. What we need to know is we need to know important things about the velocity and the acceleration. We'll start with the formula. So the velocity of an object moving in a circle at a constant speed is given by 2 pi r, which is the circumference, divided by t, the period, the time for one complete circle, and the acceleration, the centripetal acceleration in this case, that's the acceleration you have when you're traveling in a circle, that's given by v squared over r. We also want to think about the direction, okay, and so whenever we have an object moving in a circle, our velocity is always going to be tangent to the circle. So if we're moving counterclockwise here, our velocity at any given point would be a tangent line to that circle, and the acceleration always points inwards towards the center of the circle, and that's actually what centripetal means, center seeking. All right, some tips for solving circular motion problems. First of all, circular motion problems are really just force problems. We just have a different kind of acceleration, that inward centripetal acceleration. So we want to set up our free body diagram and our F equals ma like we would for any other force problem. Keep in mind that our acceleration is always inward, and we can find it by using v squared over r. That's really the only difference. Otherwise, it's just like a regular force problem. Moving on to projectile motion here, the most important concept we need to know about projectile motion is the motion in the x and y direction. And so in the x direction, we have a constant velocity, which means our acceleration is 0. And in the y direction, we have a downward acceleration of 9.8 meters per second squared. This object is in free fall. The only force acting on it is gravity, so therefore it's accelerating down at 9.8 meters per second squared. Let's go ahead now and talk about two different kinds of launches or projectile flights that you should be familiar with. The first is a horizontal launch. There's a few concepts we need to know about that. Most importantly, we need to know that our x acceleration is 0 and our y is at negative 9.8 meters per second squared, or 9.8 meters per second squared going down. The other thing we know if it's a horizontal launch is that our initial y velocity is 0. Okay, if we launch something horizontally, that means that it has no y velocity in the beginning and only has x. And if we think about our velocity as we go through, our x velocity is going to remain constant, and what's going to happen with our y velocity is, even though it's initially 0, it's going to grow and increase as the object flies through the air as it's accelerating downward. The other kind of launch we want to think about is an angled launch here. So a few things about that. First of all, we know that our x and y acceleration are the same. If it's launched at an angle, we can break that initial velocity into x and y components. That x component is going to be vi cosine of theta, assuming it's measured from the horizontal, which it usually is. And that y component is going to be vi sine of theta. We also know that when we get to the peak, our y velocity is 0. Okay, and then we have a few concepts that are true only if it's a symmetrical launch, meaning it lands at the same spot that it was launched from. So the first one is that if it's symmetrical, our time here at the peak is half of our total time. The second thing we know if it's symmetrical is that when it returns to that same height there, that change in y, the delta y, is 0, and we know that our y velocity at that point when it returns to the same height is just the negative of our initial y velocity. But again, those last three are only true if it's a symmetrical launch. Next, let's talk about some tips for those projectile motion problems that we were just talking about. The first tip is these really are just kinematics problems, so we're going to set up our chart in both the x and y direction with our displacement, initial and final velocity, acceleration, and time. So we'll do one for x, one for y. We always know the accelerations, okay, and we always know that the times can transfer from the x to the y. That's the one thing that doesn't really have a direction and can go between the two sides. We want to really think about our concepts. They're even more important with projectile ones than with kinematics. You know a lot of information even if the problem doesn't explicitly state it. And of course, like with anything, we want to be careful with our signs. Next, we're going to move on to energy here. And so for energy, we're going to talk about first the basic types of energy, the formula for those types, and when an object has it. So we'll start with kinetic. Kinetic energy is given by 1/2 mv squared, and objects have kinetic energy when they are moving. That's the key idea. Gravitational potential energy is going to be given here by mgh, and objects are going to have gravitational potential when they have a height. Spring potential energy is 1/2 kx squared, and that obviously exists when there's a spring being stretched or compressed. For work, we actually have two definitions. So the first one is this: work is the change in energy that results from a force. We can find it from that force by doing F delta x cosine theta, where theta is the angle between force and displacement. Or we can say that work is just the change in energy, and that's really what the meaning of work is, the change in energy that results from a force, so it's just delta E. And we're going to have work being done when there's some force being exerted on an object. That's when we have work. Next, we're going to talk about conservation of energy, which is really the big idea when we're dealing with energy. And so I'll start with the formula here. energy initial, the total initial energy of an object, plus any work done by non-conservative forces, and we'll do a refresher on that in a second, is going to be equal to the final energy of an object. So really what this equation says is that energy is conserved. It's neither created nor destroyed, and the only way objects transfer energy is through work. So if we take the total initial energy that an object has, plus any changes to that energy because of work, it's going to give us the total final energy of an object. And so we're going to use this equation when doing conservation of energy problems. So let's talk about some tips for those problems. First of all, we want to think about what kind of energy the object starts and ends with. Does it have kinetic? Does it have gravitational potential? Does it have spring potential? Okay. We then want to think about, is there any work being done by a non-conservative force? Okay, so do we have maybe friction or a push or a pull doing work on the object? And then we're going to go ahead and sub in all these equations here into this equation. It's kind of like F equals ma, where you have to make your own equation based on the specific energy types that are present in the problem. Okay, so let's talk about this conservative, non-conservative piece. Basically, when dealing with energy, we have two kinds of forces. First kind is conservative forces. These are forces like gravity and spring forces. Those are really the two big examples. And the reason why they're conservative is the work done by those forces can be undone. Okay, and so rather than saying that as a ball rises to its peak, gravity does work on it, we say that that energy just becomes gravitational potential energy. So we don't really think about the work done by gravity or the spring force. We think about the potential energy associated with that force. On the other hand, a non-conservative force would be something that where the work cannot be undone, like friction or a push or a pull. Those are really the big examples there. And so in those cases, we will need to think about the work done, and we will need to put it into our equation here, because they actually do change the energy of the object. All right, so we're going to move on here to talking about momentum. So we have two formula for finding momentum. The first is just that momentum is equal to mass times velocity. That's just the basic definition of momentum. And the other important one deals with conservation of momentum, which is one of the two reasons why we really care about momentum, the other being impulse, which we'll talk about in a second. Okay, so conservation of momentum tells us that the initial momentum of a system equals the final momentum of a system if there are no outside forces. Let's talk about a few tips here for solving these conservation of momentum problems. Whenever you're doing these ones, it's kind of like setting up conservation of energy. We're going to think about what in the system has momentum before and what has momentum after the event. And usually what we're talking about with momentum is either a collision or an explosion. We're going to be careful with the sign of our velocity because momentum is a vector, as is velocity, and we need to indicate that with a sign. If we have a case where the two objects stick together, what we usually do is we just combine their masses and treat them as one. The other thing we're going to talk about here related to momentum is impulse. So impulse is the change in momentum. It results from a force being exerted over some period of time. And so conceptually, impulse tells us that when we have a longer collision, okay, longer time-wise, it decreases the amount of force. And this is what we see in a lot of safety devices. Extending the time of the collision decreases the force. Mathematically, we have three ways of finding the impulse. So impulse is either mass times change in velocity. Momentum is just mass times velocity, and velocity is the thing that's going to change in almost all situations of those two. Or we can say that the change in momentum, which is the impulse, is the average force acting on an object multiplied by the period of time over which that force is acting on it. Or we can say that the impulse to change momentum is going to be the area on a force versus time graph, okay? The area under the curve. So that's the third way of finding the impulse. All right, so we're going to start talking about rotational motion here. And as you remember, a lot of the things we did with rotational motion were the same. The concepts are really the same as linear motion. There's just a few little twists and tricks here. So let's start with rotational kinematics and start by identifying the new variables, our rotational kinematics variables. So instead of delta x, our displacement, we have delta theta, our angular displacement, which is measured in radians. Instead of v initial and v final, we have omega initial and omega final, our initial and final angular speed, which is measured in radians per second. And instead of a, our acceleration, we have alpha, our angular acceleration, measured in radians per second squared. All right, and we have our four kinematics equations in rotational world. They are exactly the same. We just replaced the variables. So we have our delta theta equation, our omega final equation, our omega final squared equation, and our other delta theta equation. The other thing that's really important when thinking about rotational is the link between linear and rotational quantities, and the key in all situations is the radius. All right, so this really comes into play in two situations. One, when we have an object that's rolling smoothly along the ground, it has rotational speed because it's rotating. It also has a linear velocity because it's moving. The other time when we see it is when we're thinking about an object spinning, rotating in place, and we think about the motion of a point or some object sitting on that rotating object. That object has a tangential velocity while the object rotates. So when we have those situations, the link, like I said, as always, is radius. So we can say our displacement is equal to our radius times our angular displacement, our velocity is radius times our angular velocity, and our acceleration is radius times our angular acceleration. All right, so moving on here to dynamics, and starting with torque. Torque is an off-center force that causes rotation. All right, and the following factors are going to affect the amount of torque, the amount of force we have, the distance from the pivot, and the angle between the force and that radial distance, that distance from the pivot to where the force is exerted. And it's maximized when the angle between them is 90 degrees. Equation-wise, the way we find torque, torque can be found with this equation. Torque equals R F sine theta, where again that theta is the angle between the force and that radial distance. Next we have moment of inertia, which is really just the rotational equivalent of mass. Okay, it represents how difficult it is to make an object rotate. And it depends on the amount of mass we have and how that mass is distributed and how far it is from the pivot. Combining these two ideas, we lead to Newton's second law for rotation, which tells us that the sum of the torques is equal to I, the moment of inertia, times alpha, the angular acceleration. Okay. A few tips here for doing these problems. The first thing I would do, they're very similar to F equals ma problems. I would draw all the forces and also consider where they act. That's the one thing that's different. We need to think about how much force we have and where that force acts. And then think about setting up your sum of the torques equals I alpha. Okay, and going from there and setting it up just like you would a regular force problem. We're often able to calculate the amount of torque using this equation here, and that can lead to figuring out the angular acceleration and doing kinematics and all that good stuff. One last thing to consider for this is the direction. Okay, we always consider that, and our signs go along with that directional piece. But in rotational world, clockwise is considered to be negative and counterclockwise is considered to be positive. Like anything else, it really doesn't matter as long as you're consistent, but that is the standard. Moving on to circuits here, we'll start with our two basic equations for circuits, which are Ohm's law, power, and our definition of current. So Ohm's law tells us that voltage is equal to current times resistance. Our power law tells us that power is just voltage times current. And lastly, we have the definition of current, which is that current is just the amount of charge, delta Q, over our time. Okay, we're going to talk then about the three main variables, voltage, current, and resistance, what they are, how they behave in series, how they behave in parallel. Okay, so let's start with voltage. Voltage really represents the energy of the electrons as they travel through the circuit. A 9-volt battery versus a 1.5-volt battery means that the electrons in the 9-volt battery have more energy. Okay, and voltage is something that gets lost as they travel around. So electrons start with 9 volts of voltage or electric potential, and when they return to the battery, they've lost all of it. In series, the way voltage works is that the total voltage, the voltage provided by the battery, is equal to the sum of the voltages across each resistor. Okay, and that's just in a basic series circuit. In parallel, what we find is that the total voltage is equal to the voltage across each resistor. Okay, just as a quick refresher, a series circuit is one where you have one resistor right after another, whereas a parallel circuit is one where there's two separate branches and they are parallel to each other or in parallel. Current, that represents the charge flowing through the circuit. It's like the flow of traffic, all right, the amount of charge or the number of electrons. The way current works in series is in series, the current is the same, all right, through each resistor, and that really is just because the electrons have nowhere else to go. If they flow through that first one, they have to continue through the second one, and so on. In parallel, however, that total current, the current leaving the battery, is going to be equal to the sum of the currents across each resistor. And again, this would be in a simple parallel circuit, where it's just 2 or 3 resistors in parallel with each other. We're not really going to do combination circuits for this final review here. Resistance, our last quantity, that is how much a particular element in a circuit resists that flow of charge. Okay, and the way it works in series resistors combine and we add up their resistances to get the total resistance of our circuit. In parallel, we have that weird 1 over equation, that 1 over the total resistance equals 1 over R1 plus 1 over R2, and so on. The last thing we're going to think about here is simple harmonic motion. So we'll talk about a few things related to that. So the first thing is just the basic relationship between frequency and period. The frequency is how frequently oscillations occur, and the period is the time for one oscillation. Okay, and so they have an inverse relationship that frequency is 1 divided by the period. If we're talking about a pendulum or a mass on a spring, we have a way of finding the period for those objects. So for a pendulum, it's 2 pi times the square root of L, the length of the pendulum, over g, the acceleration due to gravity. And if we're talking about a mass on a spring, the period is 2 pi times the square root of m, the mass of the object on the spring, divided by k, the spring constant. Lastly, we want to talk about that transfer of energy when we have a pendulum or a mass on a spring. And for both of them, we actually get the same transfer of energy from kinetic to spring potential or gravitational potential and back. Okay. So for a pendulum, we start here with gravitational potential. As it swings down, it becomes kinetic, and then back to gravitational potential, and the whole process repeats itself. For a spring, let's say it's fully compressed on the right here, we start with spring potential. That gets transferred to kinetic as that spring releases, and then back to spring potential once again, and it would oscillate back and forth. So we do need to know about what that transfer of energy looks like.